If you haven't done so already, I would like you to pause the video and attempt the warm-up, which are numbers 1 through 5 of your 4.5 Day 1 notes. Hit play when you are ready to check your work. Number 1, you had to write 27 to the 4x power as a power of 3, which means you would rewrite 27 as 3 to some power. 3 cubed is 27. So when I write it as 3 cubed raised to the 4x power, this is a power to a power, meaning I multiply them, giving me 3 to the power of 12x. Number 2, if you were to ask yourself, 5 to what power gives you 4, it's not going to be a nice solution. So you had to use the change of base formula. Remember, it's log of x over log of the base, so log of 4 over log of 5. You'd have an approximation of 0.861. Next, you were asked to simplify 4 squared to the power of 2x minus 3. When you have a power to a power, you need to multiply. So we had 2 times 2x minus 3 in the exponent. And we would have to distribute the 2 to each term is what you see here. So 2 times 2x is 4x. 2 times a negative 3 is a negative 6. You actually could simplify further, so if you left this as your solution, it's technically incorrect because 4 can be rewritten as 2 squared. If you rewrite it as 2 squared, once again, you would have to distribute that 2 to each of the terms because we can multiply these exponents together. That's the power to a power property. So I'd have a base of 2 and 8x minus 12 as the exponent. Number 4, we have 3x equals 5. Then log base 3 of 3x would equal log base 3 of 5. So I wanted to show you that if I'm going from here to here, the difference between 3x and log base 3 of x is that we took the log base 3 of it. So I wanted to show you what you do to one side, you do to the other. You use that a lot when you're solving in Algebra 1. It's the idea of using the inverse property. If you're adding 4, you want to subtract 4. If you're multiplying 4, you want to divide by 4. If you have 3 as the base of the exponent, you want to take the log base 3 of that. So the log base 3 of 3 would cancel out, and I'd have x equals log base 3 of 5. Number 5, we have 10 to the log of 2x. This is a common logarithm, so I know it's a base of 10. And then I have 10 cubed here. Now, we know technically that this will cancel out, and really I have 2x equals something. But that's not what I asked you to do here. What I wanted you to do here was recognize, okay, how do I get from this to this? These two had the same base of 10. When you have the same base, what we can do is just set the exponents equal to one another. The warm-up was challenging. It was meant to challenge you. So if you didn't get any of them right, it's no big deal, okay? What's important is that we're going to take these ideas and we're going to use them in today's notes. Today you're going to learn 2 different methods to solve exponents. So here's method 1. What we're going to do here is, for method 1, if we're able to take 2 exponents with the same base, we can just set the exponents equal to one another. We saw that in your warm-up. It was number 5, you see? For number 5, we had the same base of 10, So we set the log of 2 of x equal to the 3. For example 1, we have two different bases. We have a base of 8 and a base of 2. We want to rewrite it so they have the same base. We used this idea in number 1 when we rewrote 27 as 3 cubed. So when I'm thinking about what base to use, I would say let's use a base of 2 because 8 is equivalent to 2 cubed. So I'm going to rewrite this as 2 cubed to the power of x equals 2 to the x plus 6 power. This is a power to a power, so I know I'm supposed to multiply them together. That gives me 2 to the 3x power equals 2 to that x plus 6 power. They now have the same base, so I can set the exponents equal to one another. So I have 3x equals x plus 6. And now all we have to do is solve. In order to solve for the variable x, we need to try to get it by itself. Again, this is where we use the idea of inverse operations like you did in Algebra 1. So if I want to get x by itself, I'm going to move this x over to the other side. 3x minus x would give me 2x, and I still have that 6 over here. I'm currently multiplying by 2, so I would need to divide each side by 2, meaning x equals 3. Sometimes we have what's referred to as false solutions, so solutions that don't really work out. So now we need to get in the habit of checking our work. We need to make sure that x equals 3 really is a solution, not a false solution. So we just plug it back in. Okay, so plug in to check. We're going to plug in a 3 wherever we see x in the original equation. So I have 8 to the power of x, so 3, equals 2 to the power of x plus 6, so 3 plus 6. That gives me 8 cubed. If you don't know what that is, like I said, you can plug that in your calculator. It's 8 times 8 times 8. So 8 cubed is 512. Equals, on this side, I have 2 to the 3 plus 6 power. So that's 2 to the 9th power. Let's plug it into our calculator and see what we get. 2 to the 9th power is 512. If what we have on the left side is the exact same as what we have on the right side, then yes, it does check. So x equals 3 really is a solution to this problem. Moving on to example 2. We want to rewrite it so that they have the same base. So when I think about it, I'm like, okay, well, I have 4 and an 8. 4 squared is 16, so that won't work. And then 8 to a power won't give us 4. There isn't really a nice way to rewrite it. So what we're going to have to do is rewrite both exponents. So how can we get the same base to give us 4 and 8? Well, 2 squared would give me 4, and 2 cubed would give me 8. So I've rewritten it so they both have a base of 2. The 4 was raised to the 3x power. The 8 was raised to the x plus 1 power. When we have powers to a power, remember we multiply. So I have 2 times 3x, which gives me 2 to the 6x power. And then here I have 3 times x plus 1. Hopefully by writing it this way, you can see that 3 needs to go to both of the terms inside of the parentheses. So it's 3 times x and 3 times 1, giving me 2 to the 3x plus 3 power. Because they have the same base, we can now set each exponent equal to one another. So 6x equals 3x plus 3. And now we solve for x. I'm going to move this 3x over to the other side. I like to try and keep my x's positive if I can. That's why I moved it over to the left-hand side. So 6x minus 3x is a positive 3x. I still have the 3 on this side of the equation. X still isn't by itself. I'm currently multiplying by 3, so I would have to divide each side by 3, which would give me x equals 1. I need to make sure that 1 really is a solution, not a false solution. So we need to plug in our value for x into the original equation, wherever we see x. So this is 4 to the 3 times 1 power equals 8 to the 1 plus 1 power. If I clean that up, that would give me 4 to the 3 times 1 is 3, and 8 to the 1 plus 1 is 2. You should know your perfect squares by now, so 8 squared is 64. If you're not sure about 4 cubed, you can either do it in your head, so 4 times 4 times 4. 4 times 4 is 16, times 4 is 64, or you can just check with your calculator. That's okay. So 4 cubed, you can see, is 64. So yes, it does work out. Example 3, we need to rewrite it so that they have the same base. 3 would actually be the base that I want to use, so I only have to rewrite this side of the equation right here because I know that 3 cubed gives me 27. Now that I have the same base, I just set them equal to one another, so 2x equals 3. Divide each side by 2 so I can solve for x. That gives me x equals 3 halves. Or you could put 1.5 if you like. I usually think it's easier just to leave it as a fraction, but that's just me. I need to make sure that this really is a solution, so I'm going to plug it back into the equation. I have 3 to the power of 2 times x, so 3 halves, equals 27. If I kept it as a fraction, I can see that the 2's cancel. So it's just 3 cubed equals 27. 3 cubed is 27, so I have 27 equals 27. Yes, it does check.